In every generation, there's a moment where everything changes. A breakthrough that ushers in a new way of doing things and ensures the world will never be the same again. This is one of those moments. Introducing GE Additive, a new business that represents GE's passion for the industry and its tremendous potential. Its capacity to make complex parts that were once impossible to produce, to speed up the manufacturing process, and open up a whole new world of design possibilities. At GE Additive, we're leveraging digital industrial capabilities and new technologies to accelerate innovations across industries. From aerospace, power, and automotive, to medical, architectural, and consumer applications. And as a leading user of additive parts, we're committed to delivering world-class machines, materials, and services for customers around the globe. And once again, expanding the boundaries of what's possible.
Good morning. Can you hear me well? All right, wonderful. So my name is Mohammed Adashami. I'm a 30-plus years of veteran of GE Aviation, and about a month ago, I got this job to put together a new business called GE Additive. Let me take a minute and explain to you what additive is from our perspective, why we got into this space, what was our journey, and what I want to tell you through this dialogue is it is all about what we're going to do outside of GE. We are committing to manufacture, produce, and deliver 10,000 additive machines over the next 10 years to outside customers outside of GE, in addition to doing the needs of GE itself, which will be 1,000 or something like that machines. But we look at additive as transformational. Why? Because additive is where digital and physical come together. And I will walk you through how we got here and why we see such an incredible opportunity. As you're aware, we are in the process of acquiring two fantastic companies, Arcam and Concept Laser, and they're going through the legal procedures, and very soon here we will announce their acquisition. So those two companies, plus all the other technologies that we've done inside GE that I will share with you, will sum up our journey and why we want to go where we want to go. So if you look at inside GE, there are several industrial businesses inside GE, whether it's power generation, our aviation, transportation, oil and gas, or healthcare. Inside GE, we've been playing with the idea and actually demonstrating and certifying and producing additive parts for about a decade or so. And how we got here is very interesting. I'm going to take you through one journey in GE Aviation, which is dear and near to my heart. So what you see on the screen here is the GE Aviation LEAP engine fuel nozzle. The job of a fuel nozzle is to deliver the fuel into the combustion chamber and to atomize it, to mix it with air to make it burn efficiently. Traditionally, you will have to have 20 to 25 different braces, joints, welds. What we discovered was we can take all of that to one part. And you see an X-ray image of the fuel tip here. It is very complicated. It has passages as narrow as 2 or 3 times thickness of a human hair. Imagine trying to braze that, to join that. It couldn't. In 2011, 2012, when we decided that we're going to beat our competition on fuel efficiency for this marketplace, we designed this fuel nozzle. Then we realized we couldn't make it conventionally. So we started the thought of, what if we could print this? How do you print it? We don't know. So we came across a business called Morris Technologies in Cincinnati, Ohio. As soon as he printed the first set of fuel nozzles, I called my business development guy. I said, buy him tonight. He said, why? I said, look, this technology is a game changer. And making a long story short, in a matter of a month, we had acquired Morris Technologies. Then we started producing this, and we realized, oh my God, I get 25% better weight, I can get better fuel efficiency, and I can simplify the system. Then we took a bunch of engineers, 8 of them actually. We gave them an old engine. It's called CT7. It's an old helicopter engine that's been around for 30 years. We said, go take this engine and see how much of it you can print using these Morris Technologies machines. They said, let us give it a try. So they took the engine and they were able to print about 40% of the engine. They took 900 parts, reduced them to 16. Of the 900 parts, we took 30% of the weight out. We took 40% of the cost out. And from the day we told them to go until we fired that engine was 18 months and 2 days. And with very little money spent. That's when we realized, oh my God, this is a game changer. What I'm holding in my hand is a combustion chamber for that CT7. Traditionally, you will use a lot of laser machines to make each of these individual holes, and they're not uniforms. Either you use laser or you use EDM. What we did here, we actually printed the holes inside. We realized something that we've never done before. The temperature of this metal is 25% lower than the traditional manufacturing. And the efficiency of this combustor is 20% better than traditional manufacturing. And the reason this thing looks yellow, because we painted it to see what kind of temperature it actually will do inside the machine. So it's been tested, okay? Interesting enough was, we realized the potential was way beyond the fuel nozzle. So we said, okay, what new machine, what new engine is coming along, and what can we do with it? So came along our advanced turboprop engine. This is an engine that is gonna power the Textron airplane called Denali. It is being developed in Europe, actually, in conjunction with Italian, German, Polish, and Czech colleagues of all of my engineers. This engine will have, using additive, will reduce 855 parts to 12, take 5% of the total engine weight down, and interesting enough, it will be 20% better fuel efficient than the engine today that it replaces. We're gonna fire it in the 3rd or 4th quarter of 2017, and right now we are producing a lot of those parts as we speak. Now, let me show you a couple of things from that engine. This is an exhaust cone. Traditionally, the thickness will be about double of what I got in my hand. But using additive technology, we can put these stiffeners, ribs, print them in. When you print that in, you don't need all of that thickness. This is 50% lighter. If it was the traditional manufacturing, I couldn't lift it with my hand. I'm a 60-year-old man. I couldn't lift that big of a part, okay? The other part I'm not gonna lift. Well, maybe I do. We took 80 parts, and we printed them all together. This used to be 80 parts. Now it's 1, okay? It's a sump and bearing support for ATP, okay? Again, you see the stiffness, and you see all the assembly has gone away. We used to have 5, 6 different suppliers to create this. No more. Want to make sure I didn't drop it. So one other thing came along. Traditionally, we do a lot of big casting for aviation engines, front frame, mid frame, rear frame. Our supplier called, said, Mohammed, when are you going to order your castings for this machine? I said, I don't think we do. I said, are you crazy? I said, no, we're going to print it. And that is the game changer. That's the revolution for us, okay? As I speak in front of you, the fuel nozzle is in production. It is on A320neo that's been flying around the world for the last 4 or 5 months. It will be, and it is actually testing for 737 and for Chinese C919. We also have a sensor, T25, for our GE90 in production, and we've got 2 other parts for other people that we print that I'm not allowed to tell you, that they are also in production, okay? Now, when you do look at aerospace, you see one opportunity. Then we started looking outside of GE. What you see on the screen here is a acetabular cup. It is a hip replacement for human being, okay? And I got it here, actually. It's a ball and a socket. This goes inside the leg. This goes here. You got a joint here, okay? The trabecular joint is a resemblance of human bone, allows the human tissue to grow into this, and there's a huge opportunity in here. You can do 2 ways. You can either customize it, tailor it per person by scanning, or you can have a standard production for many and many and many, okay? The way this cup is actually printed, we print 7 of them at a time. 1, 2, 3, 4, 5, 6, 7 of them at a time, okay? So mass production and quite fast. So these are titaniums and things like that. One other thing I want to show you, this is produced in Europe by one of our machines. This is a oil pump for a motorcycle. If it was traditional manufacturing, it would be a lot of parts, and this would weigh twice more than what it weighs today, okay? What else can I tell you? Oh, 2 more. So any machine that creates or consumes energy had a heat exchanger on it. You put air or oil or water through it, and then you cool the engine or you cool the machine. We printed a honeycomb that resembles the inside of a heat exchanger. And right now, for our GE9X, we are producing the heat exchangers. And we realized we got 25% weight out, a lot more fuel efficiency, and significant collapse of the schedule as well. What I got in my hand is a low-pressure turbine blade. It's made out of titanium aluminide. It is produced by our Avio Aero team in Cameri in Italy, okay? And using RCAM machines. This thing is incredible. It is fast, it is accurate, and it is light. It takes a lot of the weight out. For flying engines, you need a lot of lightweight. Sorry, guys, with the sound. So look, with traditional manufacturing, when the design sophistication increases, the cost of manufacturing, the cycle of manufacturing, and the complexity of manufacturing increases. With additive manufacturing, it's not so. The cost actually goes down. The cycle goes down, and your manufacturing supply chain actually gets simplified. What you see on the video here, it is printing layer by layer using DMLM. When you're printing, you are putting 50 to 100 micron of a layer at a time. When you're doing that, you're actually using a 3D model, a CAD model that you have created. And a CAD model is a bunch of ones and zeros that you're creating and sending to the machine, and a physical entity comes out of it. When you do that, you are creating a digital twin. The digital twin has a lot of data in it. That data is captured in the cloud, and in our case, on our predicts. And then we can analyze it and predict how the machine or how the part will behave as you go forward. So where do we see the growth? We see a lot of growth in materials, and as you know, GE has a tradition of being very good in material science. Remember, our grandfather is Thomas Edison, the guy who created a lot of stuff. We see growth in machines, and our machines will come to market with predicts already built in them. So if the customer wants to use them, it already generates the data you want and also analyze it for you. And then with engineering, these are engineers who are application engineers that will send them to you with the machine to show you how to use it, how to design it, how to analyze it, and how to optimally make sure you create your parts. Now, early on, I told you about the GE businesses that use additive, but this is the larger global ecosystem. So whether it's in GE Aviation Additive Center, which is in Cincinnati, this dot, and by the way, we simplified. I actually took a lot of dots off of this chart because it was getting too crowded. You know, we got a center in Pittsburgh. This is where in Auburn, Alabama, right? Right. Where we're producing our fuel tip, to our GE Oil and Gas, to Avio Aero, and all our global research centers around the world, whether it's in India, or it's in New York, or Munich, or China. All of our engineers, we have 50,000 plus engineers and scientists, and we want to make sure everybody gets a chance to play with this technology. We also, yesterday, we released a press that we're going to put $10 million to donate machines to elementary and secondary schools for the kids so they can grow up with it. They can print plastics, and they can play with it. We also will choose 50 universities and colleges around the globe to give them machines so the university students can play with the machines and understand how this technology can be harvested for the better of our future, okay? And then I think finally, how do we enable this through predicts? The blue lines here are showing the ones and zeros. Again, from the mind of a designer through a 3D CAD model, you create that 3D model, send it to a machine, and that beautiful blade comes out on the other side. And the machine works 24/7. Now, the trick is going to be, how do you make sure these machines and the materials and the products are certified for the right industry? At GE, we have an aviation system, we have a healthcare system, we know how to deal with the regulated industries, and we can help to get there. So at one point, I told you about the 10,000 machines. These 10,000 machines are for outside of GE. And we will provide all the technical support, product support, engineering, and everything else that you need to make sure your machines are delivered on time and you are well taken care of. I think I have time for a couple of questions. Otherwise, I'm good.